All right, Charles, can you work out these numbers?
I can. So the first one's pretty easy because we did that once when we were talking a couple of slides back.
We did.
We just look at the case where storm is said to be true. Those are those two mega rows there, and they're 0.25 and 0.4. We just add that up, and we get 0.65. Worth pointing out that since we know that S is 0.65, we know that not S is 0.35.
Good.
Okay. Even though that table really has two numbers in it, we only need one of them.
Right, yes. Very good point.
Because it's constrained by needing to add up to 1. And then we do something similar with lightning. We look at the cases where lightning is true and S is also true.
Yep, there's just one case like that, huh?
There is only one case like that.
Right, but what we really want to know is what's the probability that lightning is true given that storm is true? So we need to think about both cases where storm is true and say, of these, what's the probability that that lightning is true?
And it's 0.25 over 0.65.
Right.
Which is 0.385 rounded up.
Okay. You're a cowboy.
Right, which means that the probability of not L given S is 1 minus that, or 0.615.
That's right.
Okay, so we do the same trick with probability of L given not S. So we find the case where lightning is true but storm is false, and that's 0.05, but we have to do it out of both cases where S is false, and so it's 0.05 divided by 0.05 divided by 0.35, which is 1/7, and 1/7 is approximately 0.143, rounded up. And so not L given not S is 0.857.
Nicely done.
I use subtraction in my head.
In your head, yeah.
Okay.
But it was like with carries and stuff. That was nice.
Yeah.
So, so let's see. And does these sorts of things make sense? So if it's not a storm, it's kind of unlikely that we'll see lightning.
Right.
If there is a storm, it's moderately common that we'll see lightning. Okay.
Right. That makes sense. Okay, good. So now we do the same trick again with thunder, except now instead of looking at L and S, we look at thunder and lightning. So we need to look at the case where thunder is true and lightning is true. So that would be that's all the cases where lightning is true, so it would be 0.2 divided by 0.25.
All right, and why are we just looking at the case where storm is true?
Actually, why are we doing that?
Because it's conditionally independent of storm,
It
given
doesn't
that
matter.
other information, so it doesn't matter which rows we look at. What matters is we look at a case where thunder and lightning are both true, and we compare that to thunder is false and lightning is true. So that's this number. Those add up to the 0.25. We get the 0.2 over the 0.25, which is 0.8.
Right.
So it's very likely to hear thunder if you see lightning.
That makes sense. And there's only a 20% chance that you don't hear thunder when you hear lightning.
If there's lightning, not thunder. Yep. Mm-hmm.
Mm-hmm. And so we do the same thing in the case where we have thunder and there's not lightning. So we find that row.
Okay, not lightning, and there is thunder. There's one.
Right. And we do the same trick we did before, and we get 0.04 over 0.4, which I think we did last time, actually, and we get 0.1.
We did. So if there's not lightning out, it's very unlikely to hear thunder.
Right.
All right, and just to drive this point home, that was great. Just to drive this point home, what if it was the case that it mattered what value storm had? How are we going to fill in this table?
Well, we'd have to look at a lot more rows.
Well, in particular, we couldn't draw this kind of belief network if that were the case, right? Because it wouldn't be conditionally independent. So we'd have to draw basically another edge here, and what that represents is that thunder, to work out what the probability of thunder is, you have to look at storm and lightning, all the joint combinations of those to make it work.
And that grows exponentially as you add more and more variables.
And that's right, and that's something that threw me when I started to look at this, because the picture looks a lot like a neural net, right? In a neural net, you've got these nodes, you've got arrows going into the nodes, and when you have a bunch of arrows going into the same node, you just end up like adding all those different influences together, weighted by what it has on the weight. This belief network representation is an entirely different animal. In particular, now what we're really saying is, to work out the value of this node, you need to know what's going on in all combinations of what the inputs are. And so, as you pointed out so astutely, that grows exponentially as you have more variables coming into the node, higher in degree.
So this is not just a network, it's a graph. And so we can talk about parents and children, right? So basically, the number of numbers you have to keep track of is exponential in your parents.
I mean, yes, though it's not exactly a tree. It doesn't have to be a tree. So the parent relationships are kind of weird. Like in particular, if you use parent terminology on this graph, what you're saying is that lightning has one parent, which is storm, and thunder has two parents, which are storm and lightning. So storm is its own grandfather and parent.
So let me ask you a quick question, Michael. So Earlier on when you were describing this graph, I noticed you used the word dependencies. You said we're going to capture the dependencies. So if you erase the red line between storm and thunder,
I'd be happy to.
so you erase that. Should I read this as storms cause lightning and lightning causes thunder?
You can do that, but you'd be wrong.
Oh, okay.
You can't infer that there is a causal relationship just because there's an arrow between them, right? So these arrows really are just telling us about the relationships between the probabilities and not necessarily anything about the physical processes that underlie them.
Okay, so let me make certain I understand. So what you're saying is it would be very natural to look at a belief network or a Bayesian net or a Bayes net or a graphical model and read the arrows as causes and therefore read them as talking about dependencies. But actually what's happening here is that these things represent conditional independencies. So it is not true that lightning is dependent on storm and thunder is depending on lightning, so much as it's the case that storm and thunder are conditionally independent given lightning.
That is a good point. I guess I never really realized that dependence, you use the word dependence, sometimes it means a physical dependence, like in the real world it's dependent. Here I'm just talking about statistical dependence. It's really just talking about the fact that we can derive numbers from other numbers and not that, things cause other things. So yeah, that's a really good point. It seems like that was an easy place to get slipped up.
Okay, cool.